right, so a little bit about the quest. And as you know, this is basically a regional quest in the United States because this is where the majority of the NASA moon trees or the Apollo 14 moon trees are located. But this quest began on the 21st of June, 2023, and it runs for 3 months until the 21st of September, 2023. And I'll pop that link, that URL in the chat in a bit. But a couple of cool things about this is that with this quest, we have a couple things that, that we're focusing on. And I mentioned this last one, but I just want to remind people about this. Since this is a regional webinar, and this doesn't mean that you have to live in the United States to do this. I know that a lot of you are coming from outside of the United States to the Globe annual meeting next week in Denver, Colorado. And in that area, there are different types of species related to the NASA moon trees. Douglas fir, potentially loblolly pine, sweet gum, sycamore, and giant sequoia. These regions and states that we focus on for this quest are basically what's called using the geofencing tool on Globe, where we look at the natural range of these tree species, and we focus this for the quest. So with this two-part challenge, we have one goal is to take tree height observations using the NASA Globe Observer of the type of trees that are part of that were flown on Apollo 14. Now, I have a little disclaimer here, is that on Apollo 14, Douglas fir, loblolly pine, sweet gum, and sycamore were flown on board. We also flew coast redwood tree seeds on board, but the Artemis mission, who you heard from several webinars ago, the Artemis mission flew those 4, but instead of the coast redwood, which has a limited geographical distribution, they replaced that with giant sequoia, basically the same family, but different species. So with the quest, we're looking for people to find Douglas fir, loblolly pine, sweet gum, sycamore, and coast redwood. Now, if you are using the app and you're within 25 miles of an actual Apollo 14 moon tree that has been planted and, of course, survived and is accessible to the public, okay, the app will pop up and say, hey, here is the latitude and longitude. Here's some information about this Apollo 14 tree that you're near, and here is the address of where the tree is located. If you can safely, go find it and take a tree height observation. And we've had multiple ones happen. We've had multiple ones found. So here are some examples of some of the moon trees. Now, the top 3 are the species. These aren't actual Apollo 14 moon trees, but these are species. So this fits that objective, or that goal number 1 here, where one is in Eden, Maryland. That's actually one that I found, and it's at a farmhouse of a friend of mine. It was his grandmother's farmhouse that he now lives, but it was built in the 1700s. But there is a sycamore tree there, American sycamore, that I measured at 39.34 meters. So that's a very tall one. And he's looking into the record books that it may be the second tallest and largest American sycamore tree in the state of Maryland, but that hasn't been proven yet. And then also we had one from Waterloo, Iowa, a sweet gum tree that was measured, and then in Carlsbad, California, a Douglas fir tree. But what's really cool here, these 2 images on the bottom, and one is a coast redwood tree in Monterey, California, and that height was measured at 19.83 meters. And this is an actual Apollo 14 moon tree, so this was planted in the mid-1970s. And then in Berkeley, California, another coast redwood, which is actually Apollo 14 moon tree, measured at a very tall 33.99 meters. So these are just some examples, and there's been a bunch of moon trees, the Apollo 14 moon trees and moon tree species that have been measured and put into the Globe database using the NASA Globe Observer Trees tool. And if you happen to measure a species of moon tree, or an actual Apollo 14 moon tree, as you know, when you submit, right before you submit a tree height observation with the app, there's a comment box, and we ask you to just put in there #moontree. So we know when we look at the database, we can do a search for moon tree and see exactly where all these moon trees are coming from. I want to show you this brief video, and you may have seen this. This was highlighted by the Artemis mission as well as the NASA Earth Instagram pages. And it's an Instagram reel that we created as an introduction to the Moon Trees Quest. This went out when the Moon Trees Quest began on the 21st of June. So let me go ahead and play this. It's only about a minute long, but it's very cool.
Launch commit. Liftoff. We have liftoff with Apollo 14.
My name's Dave Williams, and I'm a planetary scientist at Goddard Space Flight Center. Stuart Roosa, back when he was in high school, for a summer job, he started working in the U.S. Forest Service and eventually became a smoke jumper, which is these guys who jump out of airplanes into forest fires that are remote and can't be reached any other way. So when he was chosen for Apollo 14, he talked to people at the Forest Service, and they came up with this idea to bring tree seeds with him in his personal kit. Circled the moon, brought the seeds back to Earth, and then the Forest Service germinated them, and then the seeds were planted all over the United States for the bicentennial. So the status of the trees now, a lot of them are unknown. People send me a lot of information, they send me pictures. Right now, we've located about 70 trees that are alive.
So one of the objectives here of this, of the NASA Moon Trees Quest, is that we want to further document exactly where these trees are, what the health of these trees are, how tall they are, and basically if they are still accessible. So that's one of the great things about this quest, is that we have people checking these out for NASA and for Globe, and bringing great data into the Globe database that that folks can use. So what I did was, with this sycamore tree, I went and this is a lot going on here. I'm not going to go through all this, but I went and I used some calculations that scientists use to to estimate basically how old the tree is and how much carbon has been stored by the tree over the lifetime of the tree. And sorry about all the squiggly red marks, but Word doesn't really like that, and I didn't go and do the spell check before I copied this page. But the size of this tree is massive. If this is one, once again, at 39.34 meters, and doing these calculations, it was an estimated that it has brought in and basically stored over 125,000 pounds of carbon over the lifetime. And the estimated tree age, which was I used equations specifically for American sycamore, that it came out to, the tree is about 254.4 years old. So that's a very old tree. So, but yeah, these are some equations that scientists use to estimate basically carbon sequestration in trees over the lifetime of the tree, and then also an estimated age. And once again, these calculations are not linear, just estimates. They're not, it's not probably not exactly 254.4 years old. It's an estimate based upon the numbers that we plug into to this. So just want to showcase that. So with that said, one last slide before we go to feature presentation. And Peter Nelson, I want you to highlight this again, because people, there are different people on the webinar today than there were last month. So if you could say a few words about this slide, please.
Glad to do that, Brian. And this really goes into what we're doing here with the Globe program and our Trees Around the Globe student research campaign. Trees have been a foundational piece that people have been trying to monitor from space since the beginning. And I was really honored to be able to be part of this 50th anniversary of the AROS Data Center. And so AROS is an acronym for the Earth Research Observation Science Center, and that's a place located in the middle of the United States, where all of this satellite imagery that we've been talking about, in particular anything related to land processes, are stored at. And I was interviewed for their podcast about 2 weeks ago now, in celebration of the generational science that we're doing here, not only in the Globe program and the education piece, but also the science. How do we actually archive and keep the data that we're collecting today relevant for the future. So I talk about that in this 20-minute podcast, and I'd love to have everybody here, use this as a way of thinking about what you're doing and the value of it, not only for today, but also for the future generations. I mean, Brian just showed some examples of how old a tree is, and he highlights how those are estimates, and those are estimates because we can't measure all the 4 billion trees around the world. And so how we do that goes back to our science and how we manage our data. And the GLOBE program is a great place to be able to practice this. And so I was really honored to be part of this 50th celebration of this AROS data center that has been archiving this data for a really long time. And it's really important to me because my dad was actually one of the original foresters on the Landsat program in 1972. And so he was there, part of that whole moon trees piece of things, because he was trying to map out where the coast redwoods were, or where the Douglas fir were, or where the sycamore trees were at that time. And so to me, these are questions that we've been asking for a really long time. And to see yourself as part of this long-lived science that forestry and trees represent is just a really wonderful thing. So I encourage everybody to use this podcast as a way of situating what we're doing in the life of a tree, those things that tend to outlive a human in many cases. And so I'm really honored and excited as a GLOBE partner that not only do we have moon trees at our Oregon State University campus where we have our partnership, but we have this connection to Stuart Rosa, actually. And he was here in Oregon as a smoke jumper. And so we not only have an original moon tree seedling that has been planted, but we also have a second generation that has come from the cones from that first generation tree that was planted. So, this generational aspect of what we're doing with trees as our example and something that tells us about the past and tells us about the future is really what I talk about in this podcast. And so instead of giving you 20 minutes here of me continuing to talk about this, go listen to some more of me talk about what we're doing here in the GLOBE program. Thanks, Brian.
All right, thanks, Peter. And I'll pop those in the chat and when you guys are presenting. So with that said, we're going to have today's feature presentation, and this is going to be all about the STELLA do-it-yourself handheld spectrometer tool. And our first speaker is the STELLA guru, as I mentioned earlier, Michael Taylor, outreach scientist with the Landsat mission in the Earth Science Division at the NASA Goddard Space Flight Center. That's in Greenbelt, Maryland, in the United States. And then Peter will come back on, and he'll talk about how we can apply some of these things that Mike is talking about with STELLA, and how Peter has used STELLA as well in his work and research. So I'm going to stop sharing now, Mike, and I will turn it over to you.
Okay, thank you. Let me try and share my screen here. Okay, there we go. Can you all see my screen?
Yep, looks good. Just needs to be in presenter mode.
It looks lovely.
Oh, thank you. Yeah, I'm gonna keep it on this particular mode.
Okay.
For PowerPoint.
All good.
Okay. All right. So my name is Mike Taylor. As Brian said, I've been with NASA for about 15 years, and I got handed the STELLA project in its infancy probably about 2 years ago, and have been leading the team ever since. The STELLA do-it-yourself handheld spectrometer was created by Paul Murrell. He's a CubeSat engineer and a heck of a nice guy. Then we have our lead scientist, Dr. Petya Campbell, and our cow val guy, Jesse Barber, and Ross Walter, who is our programmer and visualizer. He created this little rotating visualization that you're seeing here of the STELLA and the data viewer, which we will see in a minute. Okay, so STELLA's mission, I'm not going to read this verbatim, but basically we're trying to democratize instrumentation and in situ data So, the spectrometers generally cost an arm and a leg, and each one of these spectrometers costs about $200. And we've been doing some cow vow on them for probably about the last year now. We're also doing field calibration on them currently, and the numbers are looking real good. And STELLA is a nice Landsat analog here, so you can see some of the overlap. Obviously, this isn't the best graphic. We're working on it. Some overlap with the Landsat satellites here, and so you can see we cover quite a wide range of the bands that Landsat does. So we can go ahead and sort of not validate necessarily, but verify that what Landsat's seeing and what we're seeing are relatively the same thing. Okay. So STELLA's potential, basically offer new science tools and such. So STELLA is very modular. So we're looking at putting on things to make it what I like to call is sort of like your own personal tricorder, if you will. Even though that's copyrighted. So that basically like a farmer might want a soil probe on there, so we might be able to do that. They're looking at water quality, so we might be able to do that as well by popping the UV sensor on here. So this is sort of a nice base, a nice starting point for doing a whole bunch of other different fun science. I know some people want to look at it through a telescope. They want to do BRDF, they want to go underneath of canopy and all that sort of stuff and do all these various different things with the STELLA, because it is a wonderful modular, scientifically viable tool. Okay. So we have a few different versions of the STELLA. So we have the STELLA Q, which is solderless, and basically it's very easy to put together, and we give you again step by step how to build it, the parts list, how to create your own, and then how to collect your data, and then eventually how to analyze your data, which I'll show you in just a minute. We have the STELLA the 1.0 has actually been archived, and now we have the 1.1, which is has a better processor on there, and it's also got the option for a GPS and a LiDAR. Okay, so we can get to surface reflectance real easily with that. Okay, so here's the STELLA Q. So we give you the nice little PDFs that you can print out and all that, and you can basically just match up the parts to where they go, connect, and then you're ready to go, ready to rock and roll with your STELLA Q. STELLA 1.0, and the 1.1 looks quite similar to this. Oops, sorry, I clicked the button. And again, we give you the parts, how to put it together, all the fun stuff, programming, and so on and so forth, so that you can build your own and start collecting your own data. The STELLA 2.0 can strap to your phone. Okay, it's Bluetooth ready. We're looking eventually at developing a nice little app for it. Okay, and again, we're trying to keep costs low, so that's why you can see that there's some rubber bands going across there. And both the STELLA 1.1 and STELLA 2.0 are drone ready. There's a little battery that you can tuck in there, and you can barely see the battery up in the PowerPoint here, but altogether it weighs about 100 to about 180 grams. Okay, and we actually have a lady we've been working with down in Virginia named Paige Williams. She's actually been flying these on quadcopters and is at her students' building. So again, Paul, being the type of engineer and awesome guy that he is very fastidious as far as putting out as much documentation as you could possibly want for these things. And if that's not enough, we also have basically a GitHub forum so that you can ask your questions. Okay, so you can go there and basically, again, if you have ideas, questions, so on and so forth, you want to do something different with the STELLA, that's where you go, and I'll go to that in a minute. And then we have the data viewer, where you can actually connect your device up and see the real-time data come in, or you can pop out the SD chip, plug it in, and do a bit of fun data analysis. Okay, and I'll show you that in just a second. And here, again, here's the open source forum. You'll have to excuse me, this is a slightly older PowerPoint for the Stella. I haven't had quite a chance to update it yet because I've been extremely busy. I think we'll end that PowerPoint there, and I will show you some of the live stuff that I have hooked up. Let me, okay, new share. Okay, and we'll go to this desktop here. Okay, can you see the new desktop? I assume that you can.
We see a purple desktop.
A purple desktop. Okay.
Oh, well, it looks purplish.
Oh, I see why. Okay, because I didn't click share on the bottom button. I'm sorry. How about now? Better?
Yeah.
All right. Sweet. Okay. So this is the GitHub forum, again, where you can ask questions. So we have like debugging issues, the applications, what you can do with it. So we're looking to beef this up quite a bit, and you can see people have already started asking some questions and all that about the Stella. If you have any ideas, again, about adding some sort of baffle or something like that, we're always looking for new fun things to do with it. Okay, and to learn from each other. Let's see. Here's the, I'm going to show you how to connect your Stella. So basically you turn your Stella on, then you plug it in, okay? And then you go to connect a device, and you'll see a little device connection up there. And this is actually my live Stella now, just reading different things. And I have quite a bit of blue going on here. I can go ahead and get rid of that screen and pop on just the raw data if I want to. If I don't want the raw data, I can go ahead and X out the visible or the infrared and just get one or the other. Okay. You can also, turn down some of the irradiance measurements going there, so you can actually see what's going on. And you have a bunch of different fun things. And if you don't need to know how to use it, we have the nice little helper up at the top there. Okay. All right. And then if you actually want to analyze the data, we have this particular screen on the data viewer. Okay. So this is data I collected. This was at NSTA. They had a nice atrium there, and it was full sun. And I just sort of, went around the nice semicircle of vegetation. And so you're seeing my measurements as I was going along over time, okay? And then if you take a look at the NDVI data, you can actually really see, me going across where, heavy vegetation was, and then there's starting gaps down in here where it's hitting, ground and bare soil and all that. And then again, dense vegetation going across over time. And we got the reflectance coming in. We're looking at NIRV and all that, okay? And a bunch of fun other like vegetation indices, okay? And the way we do that is basically there's we sort of have a how-to on the forum, and it's going to be coming up on the website itself on how to actually do the field calibrations with these. So for field calibrations, again, since we're trying to keep the cost low, we're not using your standard Spectralon because again, it's cost prohibitive. So we're trying to use polystyrene foam instead. Okay, let me turn off the sharing screen and stop sharing. There we go. All right, so now you get to look at my face, I suppose. And so yeah, so that's one of the fun things that we're doing. So you basically you get the height, you take the measurement and of your polystyrene, and then you take the measurement of your object, and the polystyrene measurement is your calibration batch, and then the batch that you take your measurement with is what you're going to use and to get to the surface reflectance of that batch. Okay, and so here's the actual Stella Q that I mentioned. Okay, we have the 1.1 here that I have. Okay, and you can see the LiDAR is mounted right in between the sensors here. So if we go down the sensors, we have visible, we have near infrared, visible, surface temperature, LiDAR right in the middle there, and then a bunch of weather data. So we have like surface temperature and ambient temperature as well. So we were hoping to do some, like evapotranspiration with that. Okay. This particular model also, you can slide out the LiDAR mount, and we have a mount for a cuvette. so you can put it in there and do liquid spectroscopy. Like I said, we're trying to make this sort of like your own, personal science station here, if you will. And there's no reason you couldn't point this up at the sky as well. And we're looking at putting an AQ sensor on here as well. So, with like fire haze and so on and so forth, you could do some fun atmospheric measurements. So a whole lot of things going on. Okay. And I think that's about the end of my intro. I'll go ahead and pop up the site if it is already up there.
Mike, you have a lot of questions in the chat box I'd like to ask you if possible.
Sure. I suppose I can field one or two. Yeah, no, I'm good until 2 o'clock. At 2 o'clock, I have a hard out because I have to go pick up my.
Okay. Let me see where to begin here. Soldering skills, are they needed? Do you have to have a background in soldering in order to put this together?
No, I would say not. You mean it definitely wouldn't hurt to check out a YouTube video or two to, how to solder properly and all that. Adafruit really puts out a good video on the basics of proper soldering and all that. But I would say no, not really.
Okay. And one of our colleagues in Argentina, Anna, is really interested in one, and she'd like to buy one. Are there different costs associated with the 3 different variations?
Definitely. So the STELLA Q is going to be a little bit less, generally speaking. The rest of them obviously going to be a little bit more. I'd say the 2.0 is actually a little bit less than the 1.1 at the moment, but they do fluctuate obviously with like, the chip shortage and various other things. We've had to do some workarounds, but generally speaking, we've tried to make it as, the parts as accessible as possible. And if you can't find something, again, that's kind of what the GitHub is for, and we'll be checking that out as well. But last I've checked, again, I should mention another thing that we're doing is we were building actually 40 of these at the moment. We have 2 interns that are building them right now, and that pretty much I've been sitting with every day over the summer, and there will be loaning them out. So I have a huge list of STELLA enthusiasts that I've sort of collected over many different events and so on and so forth, scientists, engineers, farmers, so on and so forth, and basically I have about 500 of them, and we're looking to loan them out for about 6 months at a time, a case of 2 of them each in each case.
And if you are interested in having some international partners pilot them, how do they go about getting in contact or being on that list?
Contact me directly, and we'll see what we can do. Obviously that is a little bit harder. I know we've already got someone in Greece who's looking to build some, and I know I met a few folks from American Samoa as well. Obviously that's not international, but still.
Can you pop your email in the chat, Mike?
I don't want to give that out. Yeah.
It's unlisted.
Yeah, exactly.
Get it up there.
And we do understand that our colleague Kristen Weaver is going to be taking one to the Globe annual partner meeting.
She has one, yeah. And actually, I should also mention that the astronaut candidate school, ASCAN, and Alison Widener, they have acquired 6 and trained the astronauts for on Earth science using them. And they liked it so much that her and Karen St. Germain actually bought some for themselves that we created. If we do it, it's going to be a bit more expensive, but and we need the funds anyway. So so here's my email, and then let me put a link to the page so you all can take a look at the page.
Ryan actually went ahead and put the link to the Landsat STELLA page in there.
Okay, you did? Sweet.
Yeah.
All right.
Thank you for Ryan for doing that. A question from Jeff is, how do you plug in STELLA? How does it connect?
Okay, it's got a USB-C for the 1.1 because it's using the Adafruit 2040 chip. The 2.0 is a micro USB, so it's all USB ports, generally speaking. And that's because it uses a slightly different chip. I believe, if I'm not mistaken, the 2.0 also has like a tilt monitor and some other various fun things in there as well.
And then Joanne asked, does it come with a downloadable app because she really liked to have their students build one.
Oh yeah, well it doesn't have a downloadable app, but the data viewer that I showed up there, that's a mobile app that anyone can access. Again, we're trying to make it as convenient as possible. You can download all the files to build it, so on and so forth. And the software is free as well. It's also written in Circuit Python because again, we're trying to make it as accessible as possible so people can learn some programming. I should also mention some fun features on here. It's got a universal mount that we built into it, so you can put it on a tripod. It's also got a 1/2-inch aperture, so you can put it on a dowel rod and do canopy measurements. Again, our engineer is unreal, and so he's a fantastic guy. And then there's also some other like 3D print parts. Like there's I guess it would be a sort of a baffle, which basically helps it sit like 10 centimeters above whatever you're looking at and gives you sort of the conical profile of what you would be taking measurements of at that height, and it's completely open on one side, so you can get those measurements. And one of the things that we're looking to do is basically develop a protocol for taking these measurements and all that, and then 2, making an amateur spectral library. So our beginning step with that is that our lead scientist, Dr. Petra Campbell, is going to make some idealized, basically STELLA idealized spectral, you know what I'm talking about, spectral signatures, so that we can do some fun comparisons. So if someone wanted to look at, like concrete and compare it with our idealized version, versus theirs, they could do so. Same thing with asphalt, grass, various other things, tomato plant, So
love the engineering, how you thought of everything, not just a handheld spectrometer, but all the different things you can put it on.
It also has a belt clip. That was one of my contributions to it, and so I'm very proud of that. So basically, like I like to call it sort of like the scientist's tape measure, if you will, because it can literally be that, sort of a thing, and it'll be your first, collection of data, and then obviously, translating, how we collect data and all that sort of stuff. You can't beat the hands-on experience. You can explain it till you're blue in the face, like I do with Landsat and all that, but until someone actually goes out and is like, oh, I see how this is coming in, and then they check out the NIR and it really starts to click, you can't beat that.
Oh, we have a couple more questions, and I know there's a lot more in the chat box. I see they keep coming. So if we run out of time, if you can just look through the chat box.
No. Okay. So I got to look through the chat box.
No, I mean, we can still ask, but I know you're short time.
Yeah, no. We're good with time. I have at least another like 15, 20 minutes left.
Oh, perfect. Okay. Well, one question was, I mean, we know there's different versions of phones. You have Android, you have iPhone, then you have, these different ones for different countries. And, how many phones can it work with? And is it backwards compatible with?
As long as it has Bluetooth right now. So it's using the Bluefruit app to actually just show the data, the ART data. But again, it's collected on the SD card right now. So, but there's no reason you couldn't sync up, say, the time with your phone with, the data that you're getting, and say, get, like your, GPS coordinates, and your, a lot of phones have LiDAR now. So we're looking at, tying in with that, all that sort of fun stuff. So again, developing that program is, where it comes in. So.
One question is,
you mentioned to Global Observer photos.
Yeah, and there's a question about how to become one of your interns. We have someone who's interested.
Again, that's what I told my interns, is like they're going to be the envy of every other intern out there, because literally within the first 6 days they had a master's class worth of knowledge just chucked at them, and they're doing fantastic though. They're great.
There's one long question here. Let me just read it very quickly. Just an aside here. I attended a workshop called SWG, Space Weather Underground, at the University of Alaska, Fairbanks, in which we built magnetometers measuring aurora. The workshop brought in K-12 grade teachers. We built the devices ourselves, and she loved it. We got to keep them and bring them home, gathering data for the aurora scientists. You might want to consider putting together a class for teachers.
Yeah. And in fact, that's kind of one of the fun things that we're doing. We just actually, and that's part of the loaner program. So our team is relatively small, and again, funding is always a concern. So, part of the loaner program is sort of a, quid pro quo. Hey, you get the loaner, but we would like, the information how, how did it perform, so on and so forth. Did you develop any, sort of curricula, stuff like that with it? And in fact, we just sent out, and it was a special case because it was for America View, and they have a whole bunch of professors and all that. And I know Peter is involved with them. But we sent out 6 to Brittany Antis, and so he's like, hey, I'll develop some curriculums for you around this whole thing and all that sort of stuff. And yeah, so that's what we're looking to do is actually,
Awesome.
Thank you. And then if you check out the GitHub, I did put on some sort of different tiered sort of experiments or activities that people can do with these STELLAs.
Yeah, well, there's Joanne giving you a thumbs up because that's exactly what she wanted to hear. 2 thumbs up.
Yeah. Okay. So go ahead. All right. So I was going to say that the impetus for this whole thing is that I do like a intro to remote sensing sort of 101 in about 5 to 10 minutes, usually at the booths, where I do a slow boil from just the way light works and all that, additive versus subtractive color, and then I take it all the way up to see how NIR is being reflected off of the leaves and all that. And what that means for us, and then just translate that, and it goes through a whole spectral signature sort of thing, so that people can really be get that sort of understanding. So, and it seems like a lot of people really get their heads turned when you start bringing up agriculture. As soon as I bring up agriculture, it's usually the parents of the kids that really start to dive in and like, oh, you can start to see health of vegetation from space. Well, then you could probably do this or that or this. I'm like, yeah, that's what we're doing. We've been doing it for so long. So yeah.
Well, 2 last questions before I get to the comment that Emmanuel wrote. The battery life. That was the battery. How long is a life?
The bigger battery, this guy, I believe, is about 12 to 13 hours, generally speaking. The smaller one is like 4 to 5 hours. Okay, but that one's more for again, that would be better for drones and stuff like that. And it actually does tuck right into the sensors here. I don't know if you can see that between these sensors here. It's designed to do that. So.
Okay. Mm-hmm. And last question is, if our colleagues buy the STELLA, and then you come up with some new functionality of it, is that something that they could go in with their version and upgrade as well?
Generally speaking, yes. Again, this thing is very modifiable. So if you do come up with something that new, or if we come up with something new, we try to put out a thing about it. So one of the things that I've been doing with the STELLA enthusiasts and all that, those who signed up, is basically every now and again doing like a webinar where we go through with what's latest and greatest, what we're doing with STELLA, how things with calibration or validation are coming along. So our whole team sort of goes around and tells what's going on with STELLA, what we're looking forward to doing, and all that sort of stuff.
Jeff asked I keep saying last question, but we keep getting them. How do you sign up to be a STELLA enthusiast?
Just email me, or for the most part right now, that's the pretty much the easiest way. But yeah, when I do it at events and all that, I have a nice little sign up sheet. So
gotcha. And Peter put in the GitHub page, so that's another place for folks.
That's also a fantastic thing, and we definitely would appreciate any questions. Basically, we want to really open the floodgates on the GitHub page. It's been cracked, but we need some more people flooding it with ideas and thoughts and activities and so on and so forth. So
gotcha. Well, once again, thanks a lot, Mike. Thank you for joining us. Our last comment is Emmanuel said that he loved your Yusan boat pose at the beginning of your slides. So he thought that was pretty awesome.
Thank you.
So thanks. And like I said, if people have more questions, maybe you can look through the chat box before you have to head out.
Okay, sounds good.
Thanks. And with that, we'll turn over to Peter. So Peter, it's all yours.
Thanks, Peter. I just kind of wanted to help us make this connection because everything that we're doing here in our specific Trees Around the Globe student research campaign, fundamentally we're measuring light, right? Like, and I think that's one of those things that's really important to think about. What are we actually measuring? And I'll highlight, as Mike alluded to, remote sensing is all about making these measurements without actually touching things. And so you're talking about something that is hard to touch, hard to visualize, hard to understand. And so I am excited as an educator, as somebody who uses this sort of technology in my science, to have a way of actually talking to people about it. So this tool, it really isn't anything different than what we've been doing for a long time. And in fact, a lot of teachers have already been using a form of this type of instrument in the past whenever they talk about remote sensing. And so, in many ways, we have the education lessons. We even have the vocabulary here in the Globe program to talk about this. And I think one of the things that it does open up is the ability to do experimentations in the classroom that connect up to the same measurements that are getting made up in space, or that are actually getting made by people's mobile devices, through Globe Observer. Again, this is all remote sensing. It's all about reflected light. And so that's really a key piece here, is when you're talking about physics, or when you're talking about photosynthesis, or when you're talking about chemistry even, you can bring STELLA in to help people understand that measurement that NASA makes, which is that wavelengths, and how things respond to it. So as I highlighted, it's really important to go back to that tour of the electromagnetic spectrum, because that is foundational to understanding what the heck STELLA is actually measuring. Okay, I think that's really crucial, because numbers mean different things, and here we want people to understand that light measurements are a measurement. It has units with it, and here STELLA measures in watts per meter squared. And so there is this fundamental piece of it, and that's a really important part. And as one of the things that we have the ability to do here in the Globe program is to not just make these measurements of this is the number that I'm getting, right? Like, this example here where, okay, you have these numbers, but what do they mean? And why are you getting them? And that all goes back to the surface that we're measuring. But importantly, it also goes down to what the atmosphere is like and where the sun is at the time I make this measurement. Okay, so it really isn't good enough to just make a measurement and report that measurement. What do those numbers mean? I mean, Mike was kind of showing that earlier. Great, you can make your graph, but what is it that you're measuring? And this is where the Globe Observer land cover tool really comes in, because you should be doing these things coincidentally, so at the same time. So you actually have a picture of the thing that you were measuring. Because again, your mobile device when you take a digital image with your camera to do a Globe Observer observation, you are actually measuring your blue, green, red wavelengths, just like STELLA is doing here. So one of the things to remember is that this pavement that I'm measuring with STELLA, yes, there's a lot more measurements that are being made with this sensor. There is a violet, there is a blue, there is a green, there is a yellow, there's an orange, there's red. And then you get into all these things that we can't measure with our mobile devices. And those are those near infrared wavelengths and measurements that Mike was alluding to earlier that help us to understand the health of plants and what is actually happening outside of what our camera can record. Okay, so but the great thing is our mobile devices can do a sample of what STELLA records. So what I mean by that is the blue light that you are measuring when you take an image with your camera is similar to the blue light that is being measured by STELLA. Same thing with the green light, is being measured there, and same thing with the red light. And so when you have a student do a digital image, you're actually making similar measurements as STELLA. It's just that we're only able to measure 3 of the wavelengths. And STELLA, because of the sensors that Mike was showing us earlier, it's able to break that sunlight into a lot more wavelengths and therefore be able to make different measurements. One of the things that I really like about STELLA is that not only are you getting the spectral wavelengths that are coming off of this, but I think importantly, we're getting a surface temperature measurement. And that is really important as we start thinking about, what is the importance of making using Globe Observer to make a photo, take a measurement of that pavement. Well, one thing that we can do is we can use the STELLA measurement here of 41 degrees surface temperature. That's really warm, 41 degrees Celsius here. If other students don't have a STELLA, but they're able to make to record the photos of what's in that location, we can actually start putting together the STELLA wavelengths together with the photos. And that is exactly what scientists are doing, is they take a spot measurement, just like what I'm doing here, and they can associate these other numbers with this black pavement that's there. We can also go to other surface measurements and go to the opposite side. And here you can see, STELLA can, those sensors can measure highly reflective surfaces like our snow, or areas that are not just clean surfaces, but a mix of things. Here we have dirt on top of snow, which changes those measurements. And again, if you don't happen to have STELLA, but all you have is this photo behind it, if we have that library of measurements, of coincident measurements like this, we can extrapolate from these points where we're making our measurements to other locations that have a similar ground photo to this. And that's exactly what what scientists are doing when they are using satellite measurements. Satellite measurements really are just lots of these individual measurements put together in a systematic way. Okay, so one thing I've been doing is going around and not only recording the STELLA measurements here, but I've been using my Globe Observer land cover tool and the Globe Observer clouds tool to both to make measurements not only of the ground that I'm measuring or the feature that I'm measuring with STELLA, but importantly, what the sky conditions are like. Is there smoke in the sky? Is there clouds in the sky? Where is that sun angle at that moment when I'm making this observation? Those are really important things to record with these measurements. And so I just kind of want to, I've been going around making these coincident measurements myself, including hot springs and hot water. One of the other things you may not think about is it's not only the ground surface, but it's also the color of things like tree bark or the rocks in that area that actually make up that STELLA measurement that you are making. And so when by us as a community doing a lot of rapid measurements with our Globe Observer, both in the photos as well as telling us about what's on the ground or what's in the sky, these STELLA measurements actually take on real meaning. And that's exactly what we're seeing when we start going to different things like all of the satellite measurements that you see from space. And, the big thing here is that these satellites are just seeing more ground than what you're able to do when you are standing there making your own STELLA measurement. When you are doing your STELLA measurements, like I was showing here, basically you are measuring about a 1 meter area on the ground. And so as you change that elevation of that measurement, as it goes up further into space, the area that you're measuring starts getting more reflected light into it. Okay, so that's where it really does matter what is not only what you're measuring here, but what is surrounding it, and how does the light bounce off of that to illuminate it in the way that you see when you take a digital image of that. So, what's really important is that there's a lot of things out here that we've highlighted in past webinars that we've just kind of talked about. Spectral bands are one of these things that we've talked a lot about. And this is sort of the graphic of what Mike and his team are trying to help us measure on the ground. We have the visible wavelengths over on the left-hand side. And then we have some of the shortwave information that is, again, measured by satellites because they cost a lot of money, and they have the sensors to do that. But they're also able to measure that surface temperature, and the relationship between the surface temperature and what we're measuring in the globe community is related. And that's a big reason why I'm excited about getting more of the STELLA out into the community, because one of the things that we do a lot is we show satellite imagery to students, to ourselves. And the key there is that what we are showing or what we're seeing in those satellite images relate back to those wavelengths that we're measuring and how the land cover reacts to it. Right. So as we start to bend our own minds and start to look at the world around us using these spectral measurements, using the sunlight measurements like this, we really have to understand those wavelengths and what is it that we're measuring and how do they come together. And that's what STELLA really allows us to do. And so I'd highlight, there's been 50 years of research that has been going into understanding what do you use to measure certain things. Okay, so yes, STELLA can measure a lot of different light reflection or absorption. And I think one of the things that I think is kind of exciting is the ability to actually start doing spectral measurements in your classroom. And so you can actually look at, well, what is the effect spectrally across, these different measurements when a tree seedling doesn't get enough water. And so you can actually do that experiment in the classroom where you control and you make daily measurements using STELLA here. And you can actually deprive one of those seedlings or trees or plants from water, and you can see what the spectral response is. And the reason why that's important is because we have from space a variety of sensors that we can actually already understand. And this is what Mike was saying, is not only do we want you to record STELLA or record these spectral measurements, but we actually need to know what is it that we're measuring. So in this case, if you go out and you measured dry grass, we would expect you to see, something along, that looks something like this. It would have this kind of shape to it. And the key is, what is it that you are actually seeing in your area? And, when we actually start to bring in, say, water and look at water or some other things like that, right? So this spectral profile, as we call it, is a way that we can identify different features and different things on Earth. And this is the basic thing, that we need measurements of these wavelengths on the ground so that we can understand what the satellite is actually showing us. So that's the big idea here, and I'm really excited to work with other Globe partners and teachers who are collecting this information. And there will be a difference between measurements inside of a classroom versus measurements outside when you are maybe doing other Globe measurements like tree height. And so, again, it's really important to think about where that light is coming from when you are making these measurements, and what might be happening between the sun and the thing that you're actually measuring on the ground. So that's a little bit that's I really wanted to kind of take us through and show you that there within the globe community, measuring wavelengths, measuring light has been a foundational piece of what we've been doing from the very beginning. And it's really important to start connecting not only the atmospheric protocols and measurements, but also connecting those measurements to what we're measuring using remote sensing tools like STELLA or Globe Observer. I know we've got a lot of great questions and conversations here about what we might be able to actually do with this. So I don't want to keep going on myself, because it is really exciting, this possibility. But I think one of the things that is happening here is we have the ability to have some students who are engineering focused build these sensors and get that. And then we have another group of students who are interested in just going out and making the measurements. And then we have a whole other group of students who now need a way of gathering and organizing those measurements once they're made. And this is something that I think the Globe community can really help Mike and his team with, which is building that spectral library. So as you use STELLA, don't just make those measurements by themselves, but also use Globe Observer to record what you are measuring. And again, to capture the clouds and the sun at that moment in time. All of that's really important when we do the cloud match or the satellite match to even ISAT-2 or many of the other satellite matches that we have. And so how does that 1 meter down photo that you're collecting with Globe Observer relate to the satellites? It is through this exercise that we're really excited to be able to expand that sensor in your pocket from just the blue, green, red wavelengths that we have with the photo to all of this other information that we can get. So I know I talked over, Mike has, I think, had to leave us now, but I know for me, this tool is what the Globe community has been waiting for a long time, to move from the physical touching and physical measurements into the science of remote sensing. So let's have a little conversation here about what people are thinking about doing, how all of the, some of the things that we've been talking about in our, Trees Around the Globe student research campaign, how could they come together through all of these different things that we've been measuring?
Sorry, could you say the question again? So sorry.
Yeah. So Jeff, we're really just kind of curious. I know you're one of those students who are interested in using this and working with a STELLA instrument. And I think, again, the big thing here is that STELLA is the name of the instrument, just like Modus is like the name of or that kind of thing is we have the name of the unit, and on that unit there are particular sensors. There are there was this this desire to add on a LiDAR so that we can actually know how high off the ground you're making that measurement, as well as be able to profile it in the same way that we've talked about here. So there is a lot of analog between those measurements in space, or the remote sensing measurements, and what we're trying to do here. And so I think one of the things that you saw is I actually specifically asked this group to make it possible to use Globe Observer with your STELLA measurements. And so that was the reason why you actually got the mobile device on top of the STELLA instrument, so that you can take that down image and get the imagery that goes along with those measurements. So that's what we're hoping that people will do. And I think one thing that I am going to put forward is, next week at the Globe annual meeting, as Brian alluded to, there's going to be a demonstration of STELLA that's there. As Mike Taylor was mentioning, there is, what is the protocol for using this is the question. And to me, we have a protocol already in place, and that is called the Globe Observer Land Cover Tool, or Globe Observer Clouds. And really, those two are connected together. So what I'm hoping is that after next week, after people get a chance to see this in action, make some measurements and that kind of thing, that our Trees Around the Globe Student Research Campaign will come back and talk specific protocols and research that you can do with the STELLA tool. I've already, kind of mentioned there's a variety of in-classroom activities that you can use to experiment around to see what might be a limiting factor for that tree growth, right? Brian keeps, asking us that question of like, well, is that how tall those trees are going to grow in that area? And we've talked a lot about limiting factors of droughts or water, soil, nutrients, all kinds of things like that. And STELLA gives you a way of starting to experiment around with that, so that when you look to the satellite measurements and scientists say there's a drought in this area, you will have recorded a similar profile of that in your classroom. And you can also experiment around what happens with when you overwater something, or, and so there's a lot of in-class experimentation that will help the satellite imagery just make a lot more sense, to everybody. And so I just kind of wanted to really put that out there, that I think in August, for us, we would be interested in finding out who has a STELLA, who ends up making one of these, right? And then also, if you don't have a STELLA, how can we support you in the data analysis, or, working with the data that comes out of it, which is, a lot of what we do here is we work with the data that comes off the satellites. Many of us are not the ones who are actually collecting the data. We're not the engineers. We're not the ones calibrating, right? So there's a whole group of us that can start thinking about the data and analyzing the data, and what are those numbers that we're actually getting back, and that kind of thing.
Peter, there's a comment from Joanna. She says, one, she really likes the way you made connections with everything. How you connected the relevance of using the app with the STELLA to clarify, what satellites are seen. And she said, she's like, I must have one. So she's really sold on STELLA. My question is, so are you envisioning, our partners, our teachers, students using STELLA to do research for perhaps like a research projects? And what variables should they be using to make connections between, the Globe Observer protocols and satellite observations? Because sometimes it's one thing to have something like this, but there's so much there. Teachers often think like, this is awesome. How do I use it? How do I make connections?
Yeah, Peter, you were exactly right on that. And so for me, there's the easy thing that teachers can, if you're already doing any of the Globe protocols, any of the Globe measurements, it's really easy to just add in a STELLA measurement into that and record the extra spectral numbers that you get at that. And what you'll start to see is that even throughout the same day at the same spot, you will have some differences because the sun angle is casting more shadow, or it's changing illumination as it goes through. So to me, that's an easy way that people can, if you can have a STELLA, it's just another set of numbers that you add in. But I was really excited about a few years ago when we were first starting the Globe Observer land cover piece. One of the parts that we know that we're able to see with our spectral measurements is photosynthesis change, that greenness change. And that's something that you actually see in the digital imagery as well. You can actually see when trees are stressed, the green actually goes down. Stella gives us a way of starting to think about what are those things that might affect photosynthesis. Okay. And so we know the amount of red light is an important thing for photosynthesis. So you can start playing around actually with the amount of red light and that a plant gets in a classroom. And you can have, set up an experiment where you have one plant that is photosynthesizing and has just a regular amount of light. And then you can set up another one and add in like red lights or blue lights or other things like that. And that piece of it is where you can start to see the difference between photosynthesis by species or again, sometimes the amount of carbon dioxide you can actually add into, an area that you are growing a plant in. So, really kind of starting to break down those things that make a plant photosynthesize and live and actually be able to hit that greatest height potential, right? Soil moisture, water availability, nutrients, different nutrient amounts. It really allows you to bring in that soil protocol that we talk a lot about, or that is really important in agriculture. But it can be a really hard thing to make that connection between the soil protocols that you're measuring and the spectral measurements that you get. So I really like when you do a soil a protocol, if you actually also do a STELLA measurement and that ground measurement, you are actually able to connect to the soil moisture active passive satellite and that soil moisture piece of things, because dry soil actually reflects differently than wet soil. And this is something that really came out in that by using that particular sensor. So just using the globe protocols to characterize what's there, and then using a STELLA measurement to identify it spectrally, that's what scientists do. And I'm going to share my screen again because this is one of the things that we actually, you'll notice if we go back to kind of our spectral library here, when I go to our sensors and target, you might not be able to see what's on this because of the way that the browser works or sharing. But we actually, have some different, moisture levels. Actually will change the numbers that you get back in STELLA. And so one of the things that you'll notice when you have these reference spectra is that you notice there's dry grass. Well, there's also wet grass inside of there. And that, again, will have a different profile, just like, kind of this juniper has a different profile than the dry grass. And this to me, again, has been a hard thing to connect a globe measurement, say soil moisture, to this satellite measurement. And which one do you use? And what do you use? How do you actually understand it? And a lot of times it is when you're able to make 12 to 15 individual spectral measurements like this, that you're able to make the distinction between your juniper trees versus like dry grass, or even the other type of trees that are out there. Like, for instance, I'll add in maple trees. And so even though here, this is what you start getting with STELLA, is just a lot of different numbers and a lot of different profiles. And it's just why you're getting that profile goes back to all of those globe measurements that we're making. soil moisture, leaf area. What is the atmosphere like? Is there clouds in the sky or not clouds in the sky? And I'll tell you, and I wanted to take you here to, here is a demonstration of me just kind of doing a STELLA measurement, right? And I think one thing that I want to highlight that Mike alluded to here, it is incredibly important to record how high off the ground is this sensor. And that goes back into this field of view. That's what that FOV stands for, the field of view. So how much of the ground is this instrument able to actually see? And, and so here I'm going to pause it because I found it can be really hard to read this out in the sunlight because the screen will reflect the sunlight itself. So a pro tip here I've actually found is that I will actually take a picture of my STELLA measurements so that I have a record of that, as well as touching the button here so that I can put it into the visualizer. But I like these two things. And one thing, again, there is a unit here. So you have the watts per meter squared. Okay, so you actually have a unit of measurement that you're making here. That's crucial. And then you also here, the nice thing is I have a spot measurement for this asphalt was measured at 42 degrees Celsius. The air temperature, which is different, was only measured at 31 degrees Celsius. So the exciting piece is that you can use this number to model out how hot your community is. All you need to know is how much asphalt there is in your community. And then you can multiply that by this, the 42 degrees Celsius, and that's how much area you would expect to be this temperature. And so, you go underneath a tree canopy, you'll get a different surface temperature measurement right here. And I like that you don't have to have multiple instruments to do this. It's all in one place. You add in the photo of that measurement as well. And you then have all the information you need to start understanding the surface temperature and how things like the trees or tree canopy might be affecting surface temperature, air temperature, and being able to describe your community. So I like to do those videos so that I have all of that information with me.
Well, that's awesome. We have a couple more questions for you, Peter. First, from Joanne, she asked, when she knows that we really appreciate data from pretty much anywhere, everywhere. The more data we have, the better. But yep. Is there any area, particular focus that you would like to receive data from?
Yes. Okay. So the reason why I went up and kind of showed this series of images is that we are interested in getting examples of all of the main land cover types that are in your area, right? So knowing or having measurements of your asphalt, having measurements of your concrete, having measurements of all of the built surfaces. That's what we're going for here. And one of the things to, like I said, to always think about is being consistent with the time that you're taking these measurements, because that sun angle is going to affect these numbers. So if you have a class that goes out at 3 or that goes out at 9 a.m., don't expect to have the same numbers at 3 in the afternoon. Okay, so that timing is another reason why we have a consistency with our satellite observations as well. So, going out and having a group that does the land cover photos and does that land cover piece of things, describes that, is really what we're looking for. And we want to have as much variation in our measurements as possible, meaning that I expect that at different latitudes, as you go further north or further south, we're going to be getting different measurements because of that sun angle is different over time. And this is a great way to have students actually make a connection between Earth and sun, and how the different seasons happen. Is you will actually have a different illumination number here in that same place in June than you will in December. Okay, and this is a great way to just track a location over time. And the reason why I say that is because that solar elevation here, I just clicked on a location, but this, depending on the day of the year in the north, you have just a lot more illumination depending on when you're making this measurement. So one of the things that we're interested here is to make that connection between green up, the date of green up, the sun angle, and how fast that green up occurs. And that's something that you can use with STELLA to make those measurements. And it's not just that overstory canopy that we're interested in, but it really is, kind of going back. Here's an example where you have yellow because it's flowering, and so you'll have a spike in the yellow at this time of year. And so getting when plants are flowering is a really good one. And then you'll also, if you go back later, you'll have more green at a different time of year. One of the other things that you're also measuring with STELLA is the amount of soil that is in there. And that, and it's this combination that actually gives us that number. So one of the things that I also recommend, is those, the homogeneous areas are really good. Those are really easy, they're consistent, and they make a lot of sense to us. But I'd also challenge us to go to areas where you have an assemblage of different things like this, and we call it a mixed pixel. How does that light reflection change over time? And that's exactly what you would expect to see as a tree goes through its phenology cycle through the year, right? And when it greens up at the beginning of the year, it's gonna look one way and have certain measurements. And as it goes through its leaf life, it will actually change those numbers. So it is a more detailed way of getting at the green up and the green down. And even, being able to put, right now we have paint chip colors that we use in the Globe program. Here, you can actually put those paint chip numbers to the digital numbers that we're measuring. And it gives us actually a little bit more specificity with what we're measuring. So this is kind of, this to me is the next evolution to the Globe program of going kind of from those analog protocols that we have into being able to have more digital space inside of here. And I think, when we are able to add on the LiDAR aspect, you will be able to simulate everything that we've been talking about over the last 5 years of this particular Trees Around the Globe student research campaign. And so that analog between the satellites and what you can do in the classroom is here right now. And I think part of what we're doing here is we need to experiment around with the protocol, with our numbers, to see what are the recommendations we can make. Okay, so I think the big key is for those that take on this challenge and get a STELLA measurement, is to, like Mike was saying, report back, share your results. And it really is the science of remote sensing that we've been talking about for 50 years. You make a measurement, and then you go to another place and you make that same measurement. Do you get the same numbers? And if you don't, well, why don't you get those same numbers? That really is the bottom line of what we're doing here. And this STELLA sensor like I said, I don't want people to feel left out if you don't have one. So we are going to work on helping to create that spectral library so that people and students, all of us, can contribute and start understanding these numbers that are coming through this new sensor that is being developed here. And ultimately, you know, this all takes us to where we are trying to really understand and prepare everybody for, which is the Landsat Next mission. Okay, and I part of the reason why STELLA came around and why it's really useful is because it's helping us with our Landsat Next calibration and thinking about not just the 4 wavelengths that we were talking about before, but plan on having many more satellite wavelength measurements. And so, you know, you can see this is where we're going with our science. And STELLA is a great way for us to start understanding wavelengths in those spectral measurements and how they relate to our globe measurements. Okay, so let us know if you are interested in getting a STELLA, if you are interested in working with the numbers. There's a lot of different ways of being involved here, from the engineering all the way up to the data management side of things. So don't feel that you have to have that instrument to be involved or to help us understand how to use this together with our globe measurements that we've been doing with the Trees Around the Globe student research campaign. Brian?
Yeah, one last question for you.
Please.
From Jeff, he says he's interested in helping to build STELLA sensors and engineering parts. Wait, he asked one more question. Let me look up, go up again. Students, where did it go? I see my chat box is kind of going all over this.
Went along.
Yeah, I guess that was it.
I see.
Oh, I have another question. I think it was because I have a stellar sensor. But I'm not sure how to like bring up the graph that Brian showed, I think.
Yeah. So Jeff, luckily I know we've got another way. So you and I will we'll follow up together about how to get data off of the STELLA. You know, for me, you know, there's 2 ways. One is to actually do that transfer, you know, plug it in. The other way is to take a picture of that measurement, just like what I was showing you on the screen there, and then, you know, just type that into a spreadsheet. And so I personally don't want to lose the concepts by getting hung up in that transfer piece, that technology piece, right? So so Jeff, we'll follow up with how to kind of move the data off, because that is a place where what is easiest. There's experimentation here that we're still trying to kind of figure out. And as Mike Taylor alluded to earlier, what is the best format for building up the spectral library? And so Jeff, you do need basically it comes with a USB, or all you need is a USB-C or micro USB cord. You plug that in, and then you go to the STELLA visualization website, and it should all kind of be recognized at that point. But this is one of those documentation things that the GitHub site is a great place to ask that kind of question too. So I want to encourage everybody here. We're not STELLA experts. There's really no STELLA expert out there. And that's why we're using the GitHub community forum as a place to crowdsource and to contribute and to be part of this community. Okay, so it goes under the umbrella of NASA's open science, open data. This is a place where, you know, if you come up with a better way of doing things or add something on, a new way of analyzing the data, share it through the GitHub site. And that's the place that we're trying to have that open conversation so that people can contribute and they can understand. And so no matter what age you are or where you are at, we want engineers, we want data scientists, and we need people contributing to this new sensor data set.
And the last question before we go back to Brian, and I actually have to run to another meeting as well. Before you got here, Peter, Emmanuel was talking about he had planted some trees, and he wanted to know, to measure the height and be able to see, how they're doing, if they're healthy. And you talked about a lot of variables to measure that ties into the health of these trees. And I thought that was key. And I just wanted to connect you with what Emmanuel was saying earlier. It seems like there's a lot of variables that you mentioned that he can probably start measuring that we'll talk about, or help him to understand the height and the health of the trees that he planted.
You're right. You're right on that, Peter. I mean, that to me is the power of the GLOBE program. Is there's protocols and methods that have already been developed that if you spend the time and actually use all of those protocols to measure the things, then you can go from those single points and use the satellite data and to find other places that look similar to that. And that's really the key. And so use those GLOBE protocols and use the database of the GLOBE program to organize yourself, to make it cheaper for you to actually monitor these locations. Because you're right, Peter. The methods are there, the infrastructure is there, and we just need people to make those measurements. And it then will reveal whether your plant is stressed or not, how fast it's growing or not, and you can you can do these long-term monitoring projects that you need to do when you're talking about plants growing over time, and trees in particular.